What if I told you that you could predict the next big social media trend, discover a life-saving drug, or even, I don't know, understand the laws of physics? All by grasping one simple idea. Today, we're going to unlock the power of networks with something called graph neural networks, or GNNs for short. This is the science of connections, and trust me, it's changing absolutely everything. So, what do all these things have in common? A new drug, a social network, a physics simulation? I mean, they seem totally unrelated. But the answer isn't about what they are, it's about how they're structured. At their core, they are all networks, or what we call graphs. And that's really our jumping off point. Because, it turns out that most of the world's most interesting data doesn't live in neat little rows and columns. Nope, it's a web of relationships, of connections. It's a network. So what is a graph, really? Well, fundamentally, it's super simple. You've got nodes. Those are the things, people, places, atoms, whatever. And then you have edges. Those are just the lines connecting them, representing friendships or chemical bonds or citations between papers. That's it. Nodes and edges, the whole shebang. And once you start looking for this simple pattern, you see it literally everywhere. A molecule is just a graph of atoms. A social network, that's a graph of people. An image can be seen as a graph of pixels. And even a sentence is a graph of words. All of a sudden, this one structure, the graph, becomes a kind of universal language for describing our world. Okay, but if graphs are everywhere, why can't our standard AI models, which are so amazing with images and text, why can't they just handle them? Well, it's because graphs have a few, let's call them tricky properties that totally break traditional models. Let's dig into why that is. The real question is, what is it about a graph that makes it so uniquely difficult for a machine learning model to understand? Well, it really comes down to a few core challenges. Unlike a nice, neat grid of pixels, a graph structure is, well, it's wild. It's unpredictable. But the single biggest hurdle is something called permutation invariance. Now, that sounds fancy, but the idea is simple. If you have 3 friends, it doesn't matter what order you list them in. They're still your friends. The relationship is the same. For a graph, the order doesn't matter. But for a traditional computer program, if you change the order, it looks like completely different data. And this slide shows you exactly why that's such a huge problem. See these 2 grids? They're basically how a computer would read a graph. They look totally different, don't they? But here's the kicker. They represent the exact same network, just with the nodes listed in a different order. A normal AI would look at these 2 things and think they're completely unrelated. That's a massive deal breaker. So, how do GNNs get around this? They use this really elegant idea that embraces the graph structure instead of trying to fight it. It's called message passing. The solution is just so clever. It's this simple 3-step dance. For every single node in the network, you first gather information from its immediate neighbors. Then you aggregate all that info into one single message. And finally, you update the original node with this new combined insight. It's kind of like a rumor spreading through town. Each person hears bits and pieces from their friends, combines it all, and forms a new, more complete picture. And how do you aggregate all that information? Well, you've got options. You could use sum, which is like adding up the total influence of the neighborhood. Mean is like taking the average opinion, which is great because it means a node with 1,000 friends doesn't totally drown out everyone else. And max is like listening for the loudest, most important signal in the crowd. Each method lets the network learn in a slightly different way. And the result is, honestly, transformative. Before message passing, like you see on the left, every node is just an island. It only knows about itself. But after message passing, each node is now enriched with information from its entire neighborhood. It's become context-aware. It understands its place in the network. Okay, so we've got this powerful new way of learning from networks. Cool. But what can we actually do with it? This is where it gets really, really exciting. Let's check out how GNNs are solving real-world problems. First up, we can make predictions about the entire graph as a whole. This is called graph-level prediction. We're not looking at any one piece, we're asking a question about the whole system, like, what is the overall personality of this network? A perfect example of this is in drug discovery. A GNN can look at the entire graph of a molecule, all its atoms, all its bonds, and predict something like, will this be toxic? Or will this be effective against a specific disease? This is a total game changer for medicine. All right, next, we can zoom in and make predictions at the node level.
Here, we're trying to classify individual things inside the graph based on their connections and who their neighbors are.
So, think about a social network, right? A GNN can analyze that whole web of follows and likes and retweets to figure out which users are the most influential, or maybe even spot which accounts might be bots. It's all about understanding a node's specific role in the network. And finally, we can predict the relationships themselves. This is called edge-level prediction, or link prediction. We're basically asking the GNN to play matchmaker and guess whether a connection should exist between two nodes that aren't currently linked. You ever wonder how a streaming service just knows what movie you want to watch next? This is it. By looking at the giant graph of users and movies, a GNN can predict a missing link, that you might love a movie that people similar to you have also loved. That's link prediction, right there in your living room. So, what all this really points to is a huge shift in how we think about data. We're realizing that the deepest insights don't come from isolated numbers, but from the web of relationships that connects them all. The future really is connected. The researchers who pioneered this field put it so perfectly. They defined a GNN as a system that preserves graph symmetries. In plain English, that just means a GNN is built from the ground up to respect the true nature of a network. It doesn't fight the structure, it learns from it. So, if you're going to remember anything, remember this. First, our world is built on networks, from our friends to our biology. Second, regular AI just can't handle this messy structure, but GNNs, thanks to that clever message passing idea, are designed for it. And finally, this opens up a whole new world of problems we can solve, predicting things about the whole network, the individual pieces, or the connections between them. And that leaves us with one final, absolutely massive question to think about. I mean, from mapping the human brain to optimizing global supply chains, what other incredibly complex systems could we finally start to understand? What could we solve if we could just see them for what they really are? A network of connections, just waiting for us to explore.